Observe a grand design spiral galaxy. You see a highly organized, chiral geometric structure. Its arms exhibit specific rotational symmetry and flattened disk architecture. Compare that to a massive elliptical galaxy. The geometry here is nearly featureless and isotropic. Stars orbit the smooth, central core in all directions, lacking the planar organization of a spiral. Further complicating the taxonomy are irregular galaxies. These systems exhibit chaotic, clumpy, multi-core regions with no obvious symmetric organization at all. The standard LambdaCDM cosmological framework models the dark matter halos surrounding all these galaxies as generic, spherical clouds of non-interacting particles. In this view, the diverse shapes we observe are strictly late-stage phenomena, produced entirely by baryonic processes like gas cooling, star formation, and collisions occurring inside those spherical particle clouds. Dynamic vacuum field theory, or DVFT, shifts the mechanical origin to the vacuum itself. DVFT models the vacuum as a dynamical field defined by two components: an amplitude, ρ, which dictates gravitational mass, and a phase, theta, which dictates spatial coherence. By tracking the evolution of these two components, DVFT proposes that a dark matter halo is actually a massive, matter-free depression in the vacuum's amplitude. Furthermore, the specific geometry of a galaxy, whether a spiral galaxy, a massive elliptical, or an irregular, is directly dictated by the initial geometric shape of that vacuum depression. The morphology of a galaxy is a fossil memory. We are looking at the universe's primordial vacuum architecture illuminated by ordinary matter. This 3D graph plots the pre-CMB vacuum potential. Before matter, the vacuum existed in an unstable state at near zero amplitude. Because this peak is unstable, the vacuum undergoes a tachyonic rolldown. The field rapidly descends toward the stable minimum, achieving a lower energy state. This descent happens rapidly. The roll-down outpaces the speed of light, meaning the transition occurs faster than causal information can travel to coordinate a single, uniform vacuum state across the entire universe. This limit defines the Hubble-Zurich freeze-out length, the maximum size a vacuum region can achieve while causally coordinated. The universe fractures into finite domains based on this scale. Isolated, adjacent domains settle into different phase orientations. Unable to communicate, their phases freeze entirely misaligned. A Hubble-Zurich defect is the physical boundary between two incompatible phase domains. These defects are not physical particles. They are topological scars in the fabric of the vacuum itself, characterized by sharp phase gradients where the mismatched domains collide. Long before the first atoms formed, the universe was already populated with immense, frozen topological fractures. A phase mismatch contains no ordinary mass. The physics problem is identifying the mechanism that translates a topological scar into a massive gravitational pull. In this vacuum amplitude equation, the phase gradient term acts as a massive disruption source. When adjacent domains clash, the phase gradient creates a severe energy penalty at the boundary. To suppress this spike, the vacuum locally suppresses its own amplitude, driving it towards zero. Because the vacuum amplitude governs the inertial response of spacetime, this persistent physical depression acts as a potential well. We can calculate the exact inward force using the effective gravitational acceleration equation. Any spatial depression in the vacuum's amplitude physically generates an acceleration vector pointing towards its center. Ordinary gravity requires material mass to couple with the field and drag the amplitude downward. Defect gravity bypasses mass entirely. The frozen phase geometry creates the amplitude depression directly. A local depression in the vacuum amplitude perfectly replicates the gravitational mechanics of a dark matter halo, requiring zero actual particles to function. If a defect is just a localized energy depression, physics suggests it should immediately collapse into a perfectly spherical minimum energy state. Hubble-Zurich defects carry a topological charge. They are created in a rapid non-equilibrium environment, locking their causal mismatch into place at the moment of freeze-out. This topological charge acts like a knot, physically preventing the defect from smoothing into a sphere, a transition requiring extreme energies. Denied the spherical minimum, the defect preserves its primordial multiple modes, stabilizing into oblate or prolate configurations that survive indefinitely. To map these asymmetrical shapes to observational data, DVFT utilizes a defect shape tensor. By extracting the eigenvalues from this tensor, the geometry of any primordial defect is mathematically classified into 3 principal axes, quantifying exactly how flattened, elongated, or twisted the amplitude well is. Because topological locking restricts uniform relaxation, the early universe inherited a diverse taxonomy of specific, non-spherical gravitational templates. At recombination, the universe cools enough for photons to decouple. The thick plasma fog clears, and baryonic matter is finally free to move. These free baryons encounter a universe already populated by deep, non-spherical vacuum defect wells. They immediately begin falling into them. When gas collapses into an oblate defect well, baryons are compressed vertically, naturally forming a flattened disk galaxy. If that defect carries a non-zero phase winding, it imparts rotational coherence to the infalling matter, directly forcing the gas to coalesce into distinct spiral arms. A multi-core defect, featuring several adjacent topological scars, pulls the infalling baryons into competing, clumpy centers of gravity, seeding the irregular galaxies we observe. Later baryonic processes, like stellar feedback and galactic mergers, will undeniably alter these structures, but the foundational template for the collapse was already set. Every galaxy in the modern Hubble sequence represents baryonic matter illuminating the invisible, frozen geometry of the primordial vacuum. This co-evolutionary model generates strict mathematical predictions that distinguish it observationally from standard dark matter particle models. This equation is the unified size law, defining the exact radius of a mature halo. The final size is tightly constrained by its initial Kibble-Zurich freeze-out length and the slow rate of residual vacuum relaxation. DVFT dictates that if spiral arms are seeded by phase-twisted defects, observers mapping the dark sector of spiral galaxies must find mathematical residuals of phase-twist geometry that ordinary baryonic angular momentum cannot explain. This outlines a strict architectural divide. Standard cosmology relies on vast swarms of unobservable, orbiting dark particles. DVFT relies on a smooth, continuous topological depression baked directly into the spacetime field. Deep space cluster observations, where immense gravitational distortions surround galaxies of every shape, serve as the ultimate testing ground for isolating these topological signatures. The fossilized structural memory of the vacuum itself actively sculpts the architecture of every galaxy we see.